Hi everyone. In today's session, we shall discuss the double integration method. So, in the last class, we discussed about the deflection of beam and what are the different methods to find out the deflection and the slope. So, in this class, I would like to discuss about the different cases how to solve the slope and deflection using the double integration method. So in order to that, the first case is a cantilever beam subjected to a point load at the end. So now let us take a cantilever beam with a length of L and having a point load at the free end and it mentioned to be as W. So not considering the entire beam, now let us look at a point X from the distance of free end. Okay. So with this reference point, I would like to draw the shear force ABD diagram and the bending moment. Okay, shear force on the bending moment diagram. So we all know that shear force at X point is W and that X position is minus W and bending moment will be the load into perpendicular distance minus W into X. I've taken this. So therefore the bending moment M of X is minus W into X. We all know the governing equation M by E is equal to d square y by dx square. So if I substitute M values here, so d square y by dx square is equal to minus wx by ei. So on integrating the first term, I get the slope as dy by dx is equal to minus wx square by 2ei. So we all know that integration of x dx is x square by 2 with the formula of x power n plus 1 by n plus 1. So minus wx square by 2ei plus a. On further integration, I got y is equal to minus wx cube by 6ei. Why? Because x square integration is x cube by 3. So 3 into 2, 6ei plus ax plus b. So now I will take the different conditions from x is equal to 0 to L something and I will get the constants a and b. So for in order to finding the same what I mentioned, for finding the constants a and b, now I take the boundary conditions. At first position, at x is equal to L, I'll take the deflection. We all know at as L position it is fixed, the deflection will be 0. And at x is equal to L, with respect to y x term, it will be 0. So the deflection will also be 0. So if I employ in the first equation, x is equal to 0, dy by dx. So at x is equal to L, so dy by dx is 0. So if I substitute here, what happens? X is equal to 0, dy by dx is also 0. So a is equal to WL square by 2ei. Okay. At x is equal to L, WL square by 2ei. So while employing the first condition of yield, y is equal to W minus L cube by 6ei plus AL plus B. So from this, A is nothing but WL square by 2ei. So I'm simplifying, I'm getting the W as minus WL cube by 3 into E into I. So by substituting the values of A and B in the first equation, W is equal to minus X cube by 6ei plus AX plus B. So I get it as Y is equal to 1 by EI. So minus X cube by 6ei plus A value is WL square by 2ei and the B value is minus WL cube by 3ei. So for the maximum, deflection will be taken as free end. So put x is equal to 0. So y max will be x0 means these two terms will be removed minus WL cube by 3ei. Okay. So that is the first case where the cantilever beam with concentrated load at the end. I hope it is very easy to solve. So now let us go with a cantilever beam with UDL. So the schematic diagram looks like this. So one end is fixed and the other end is free. We all know the cantilever beam means. And now let us take a position of x. So slow shear force diagram at x will be position will be minus W and the bending moment will be W into x where the load into half of the distance. So x by 2. So this is x by 2 distance, Wx square by 2. So we know that M by E is equal to governing equation d square y by dx square. So I got M as Wx square by 2. So on further simplification, I got y is equal to minus wx power 4 by 24 ei plus ax plus b. So we all know that the conditions at x is equal to L, deflection will be 0. So on integrating, what will happen at x is equal to L, dy by dx is also will be 0. So simplifying it, I can get the equations by substituting the boundary conditions in this A equations. Both the equations I got it as A is equal to wx cubed by 6ei and b is equal to minus wl power 4 by 8ei. So thus y is equal to 1 by ei minus wx power 4 by 24 plus wx cube x by 6 minus wl power 4 by 8. So the max bending moment will be, or the deflection will be at position x is equal to 0. So y max is equal to minus wl power 4 by 8 a. Okay, I hope everyone clear. So I'll go with the case 3, simply supported beam with UDL. So we all know that a simply supported beam will be having the two reactions. Okay, like this the schematic diagram. So first, in order to find out the reaction forces, as it is equally distributed, WL by 2, WL by 2. So now let us take a point X from the one end or the left end. So we all know shear force will be W by WL by 2 minus WX. So bending moment will be WX square by 2 minus WX square by 2. So the governing equations d square y by dx square is equal to m by a. Substituting the m is equal to WLX by 2 minus WX square by 2. So on first integrating, I will be getting the deflection. On further integration, I will get the slope y is equal to WL cube WL x cube by 12 ei. Deflection y is equal to WL x cube by 12 ei minus WX power 4 by 24 ei plus ax plus b. We all know that the boundary conditions at x is equal to 0, y is equal to 0, and at x is equal to L, dy by dx is equal to 0. On substituting the boundary conditions in these equations, I get A is equal to minus WL cube by 24 EA and B is equal to 5. So deflection of the beam Y is equal to WX cube by 12 minus, okay. At x is equal to L by 2 also I can get the further equation. So these are the different cases. At x is equal to L by 2, how much? At x is equal to 0. And the dy by dx slope, bending moment I have done individually. Okay. And now the case 4 is, till now we are discussing about a simply supported beam with UDL. If the load is at a particular distance from A over one end. So first, in order to find out the reactions, R1 into X where 0 to XA, and bending moment from B to C is R1 into X minus W into X minus C. So the governing equation you all know, A into D square by dx square is equal to R1 into X. So and both the conditions from A to B position I have taken and BC position also I have taken. So if I upload the boundary conditions at x is equal to 0, y is equal to 0 from position A to B and from Y to C, x is equal to L, y is equal to 0. And from x is equal to A, the slope will be from both the same portion dy by dx. And at x is equal to A, the deflection y will be same from B. Symmetry R1 is obtained as R1 is equal to WB by A plus B. So the reaction force now I got it as WB by A by B. So now I substitute the values WB by A plus B into X. Substituting minus from total L position minus W into X minus C. So on integrating, I got it as EI by dy by dx is equal to W by B, WB into 2 into A plus B x square minus W into X minus A whole square by 2 plus K2. On simplifying the equations, I can get the K1, K2, K3, K4 For the better understanding, we'll solve you in the classroom for both. Okay. So these are the some important questions asked in your university examinations. Thank you for that. And please don't mind for the distance in the class.